Have you ever stopped to think about why a political poll can be kinda accurate, but winning the lottery feels, well, completely impossible? I mean, they're both about random chance, right? But one is predictable, and the other is basically a statistical trap. Today, we're gonna dig into why.
So this is the big puzzle for today. On the surface, you'd think a poll and a lottery are pretty similar. You're just dealing with random outcomes, right? But it turns out, from a statistician's point of view, they are on completely different planets. One follows a very specific set of rules, and the other, well, the other is pretty much designed to break those rules.
Let's make this super concrete. So on one hand, we've got a political poll. We're asking 15 people a simple question. On the other hand, we've got a lottery where you choose 6 numbers and hope they get drawn. Both seem like a game of chance. So what's the secret ingredient that makes one of them predictable and the other just a wild guess? Well, the answer is something I like to call the binomial checklist. You can think of it as a set of 4 rules. If any situation you're looking at checks all 4 of these boxes, you can calculate its probabilities with some serious precision. But if it fails even one of these rules, the math gets messy fast. This is our playbook. So here they are, the 4 big rules. First, you need to have a fixed number of tries or trials. You can't just go on forever. Second, every single one of those trials can only have 2 possible outcomes. Think yes or no, heads or tails, success or failure. Third, and this is a big one, the probability of success has to be the exact same for every trial. And finally, number 4, the trials have to be independent. What happens in one trial can't have any effect on the next one. All right, let's put our political poll to the test. Let's run it through the checklist. Do we have a fixed number of trials? Yes, we're asking exactly 15 people. Check. Are there only 2 outcomes? Yep. Either they think it hurts or doesn't hurt. Check. Is the probability constant? You bet. We're told there's a 21% chance any person will say hurts. Check. And are the trials independent? Absolutely. What one person thinks has no bearing on the next. It passes with flying colors. This is a classic binomial experiment. Okay, now it's the lottery's turn. Fixed trials? Yeah, 6 balls are drawn, so that's a check. 2 outcomes? Kind of. A number either matches or it doesn't. But, here's where it all falls apart. Is the probability constant? No way. Think about it. Once the first ball is drawn, it can't be drawn again. So the odds for every single other ball have just changed. And that means, and this is the nail in the coffin, the trials are not independent. The lottery fails 2 of our biggest tests. It is not a binomial experiment, and that's exactly how they design it. So now that we actually know how to spot one of these predictable scenarios, let's put that knowledge to work. We're going to move from just identifying these things to a really high-stakes, real-world example, calculating the odds of success for a surgical procedure.
So here's our setup. We've got a specific surgical technique, and it's being performed on 7 different patients. We also know from the data that this surgery has about a 70% chance of being successful for any given person. So let's run our checklist real quick. Fixed trials? Yep, 7 patients. 2 outcomes, success or failure. Constant probability? Yep, 70% for each. And are they independent? Yes. Perfect. This means we can actually calculate the odds.
Okay, so how do we actually do the math? Well, statisticians use this thing right here, the binomial formula. I know, it looks like a bunch of alphabet soup, but don't worry about it. It's really just built on 3 simple ideas. N is just our number of trials, so 7 patients. P is our probability of success, that's our 70% or 0.7, and X is just the specific number of successes we're curious about.
So let's ask a really specific question to see how this works. Out of those 7 surgeries, what are the odds that exactly 5 of them are a success? Not 4, not 6, precisely 5.
Okay, first piece of the puzzle. We need to figure out how many different ways we can even get 5 successes out of 7 patients. I mean, it could be the first 5, the last 5, some combination in the middle. Well, the math tells us that there are 21 different ways this can happen.
All right, second piece. What are the chances of those 5 successes actually happening? Well, we take the probability of one success, that's 0.7, and we multiply it by itself 5 times. That gives us about 0.168.
And for the third and final piece, we have to account for the failures. If 5 surgeries were successes, that means 2 were failures. The chance of a failure is 30%, or 0.3. So we multiply 0.3 by itself for those 2 patients, and we get 0.09. So now we've got our 3 ingredients. We just have to put them all together. We take the 21 different ways it can happen, multiply that by the probability of the 5 successes, and then multiply that by the probability of the 2 failures. And when you crunch all those numbers, you get your answer. The probability of having exactly 5 successful surgeries out of 7 is 0.317, or to put it another way, about a 32% chance. See? We just used our playbook to figure out a precise, real-world probability. Pretty cool. But what happens if the question gets a little more complicated? I mean, calculating the odds for every single outcome one by one could take forever. Luckily, statisticians have a really clever shortcut for this stuff. So check out this new question. What's the probability of having fewer than 5 successes? Now, what that really means is what are the chances of getting 0 successes, or 1, or 2, or 3, or 4? Now, we could do this the long way. We could pull out that big formula and use it once for 0 successes, then again for 1, all the way up to 4, and then add all those answers together. But wow, that is a ton of work. There has to be a better way, right? And there is. It's a fantastic trick called the complement rule. And the big idea is this. Instead of calculating the probability of what you want to happen, you calculate the probability of the opposite happening and just subtract that from 100%. So what's the opposite of fewer than 5? It's at least 5, which is just 5, 6, or 7 successes. That's way fewer calculations. And it just so happens we know the combined probability of having 5, 6, or 7 successes is 0.646. So, to find the odds of having fewer than 5, we just do a little subtraction. 1 minus 0.646. And there's our answer, 0.354, or about a 35% chance. See how much faster that was?
So we've identified what these binomial experiments are, and we've even calculated their probabilities. But the most important skill here isn't just cranking out the math. It's learning how to spot these predictable patterns out there in the real world.
And that really brings us to the most important point of this whole explainer. The real superpower here isn't memorizing that complicated formula from earlier. The real power is just understanding and remembering those 4 conditions. If you can look at a situation and say, hey, wait a minute, that has a fixed number of trials, 2 outcomes, constant probability, and independence, you've just unlocked its predictive potential. So I'll leave you with this question to think about. What parts of your own life are secretly binomial experiments? Could it be the number of green lights you hit on your way to work? The number of times you win a round of your favorite game? Once you have this checklist in your back pocket, you're going to start seeing these patterns everywhere.